All right. So welcome everyone to this open lecture on Internet of Things. This open lecture is actually also part of a IoT course that we will be giving on distance that I will talk a little bit more about later. My name is Stefan Forsström and I'm a teacher here at Mid-Sweden University. And I'm very happy to have our open lecture guest lecturer, Jan Höller from Ericsson, who will be here to talk a little bit more about IoT in general. So I think I will just give over to you, Jan, and you can go ahead.
Okay, thank you. Thanks for inviting me here as well. I wanted to talk about, I was asked to talk about Internet of Things, and I think that what I want to touch upon is why is this happening now? Why is this something good? And what it is, what is it, and how do you actually go about doing it? It's going to be on a very high level. I cleaned out a lot of technical stuff from my material, so I hope that it's on the right level given the audience. Let's see. First, I need to flip slide, and it does not seem to work. I do like this, then it works. So a little bit about myself. I've been with Ericsson Research since 20 years. I started our IoT activities, research activities, about 15 years ago, actually. I'm doing research, but I'm also helping out in the corporate strategies, and I have some external engagements as well on the board of OMA, prior IoT or IP IPSO alliance. That was the first IoT alliance that was formed, and I'm also active in a super large industrial consortium called Industrial Internet Consortium. I'm chairing one of the working groups. I don't have an education for my job. I'm a physicist by origin, and studied in Lund, my research in physics was in mathematical physics around deformed nuclei. But anyway, here I am. I wanted to start. Usually, what do people believe about IoT, or what do people think IoT is? And now it's difficult to ask the audience and get some hands raised and hear your opinions, but many times, the popular belief that people have is IoT is a lot about gadgets. We talk about wearables, and you can see that it's actually some old stuff, some HoloLens since the 40s. Or it's more like home automation and home control. But if you look out in the industry and so on and check out what is happening there, then the reality is completely different. We are talking heavy machinery. We are talking industries that are connected. It's oil and gas, it's manufacturing, it's utilities and so on. And the players here are not the players that we're usually considering when we're going to, let's say, Shell, Clas Ohlson, or Radio Shack or whatever. It's like General Electric, we have ABB, we have Bosch. Bosch is a front runner here with good software stuff that they're working on. IBM with Watson and SAP and SAS, etc. They're all in this space, and one of the use cases that is very, let's say, in hype, has been in hype a couple of years, is predictive maintenance. I'll get back to that. And the other aspect is we talk about self-driving cars and autonomous vehicles and drones and things like that. So there's, I just wanted to, say a little bit around what people, the popular view of IoT. It's all these gadgets and things. Another thing that I want to stress as well is there's a little bit of a misconception that IoT, the thing is the device, but it is not. It's actually the heavy machine that is the thing. That is the thing that you have an interest in understanding how it's actually working. The device is the thing that you built into it or bolt on top of it. So please keep that in mind, because Internet of Devices, we have that already today. But we do not have these things as first-class citizens on the Internet. The Internet has been used mainly for people and media and video and information that is centered around people. Now we are actually taking the physical world and making the physical world first-class citizens on the Internet. Just to give an example, I will come back to some examples later on around use cases and applied areas. This is work we did with SKF. It's a world-leading roller bearing company. and they have an issue with, they have a milling process where they're making these giant rollers and the roller bearings. And in this milling process, they're cutting steel. And one of the problems that they have is that they don't know when the machines are going to fail, or when the cutting tool is going to be too blunt for actually producing quality grade material. So there's this kind of curve when you're having something that is up and running perfectly nicely, and then you can start to detect that there's actually some ultrasonic going on, and then you detect that there's some vibrations adding to that, and you might look at the oil, what is coming out of the oil that is getting, not so clean anymore, and then you can get audible noise, and then all of a sudden the machine breaks down. And breaking down means that the production stops, and that's a lot of loss of money. So we have been working with them in getting machine data. It's like 80 different data values coming from the machine from various types of sensors that can actually do, and then applying machine learning and predicting when failure might happen, so that we early on can slot when to service the machine. So this is a typical example of IoT, way beyond the consumer aspects. Now, why is IoT happening now? Well, a word from my sponsor, it's like, yeah, connectivity. We see a connectivity evolution. It took 100 years to connect places, 1 billion places basically, with backlight phones, wired phones, if anybody remembers those. And then it took 20 years to connect around 25 years to connect around 5 billion people. And now we are actually looking at connecting the rest of the world, that all the different places and all the different objects. And this is we see this evolution in the cellular from 1G to 4G, where we have mobile broadband, and now we have 5G. And then we are seeing this hockey stick curve of evolution of deployed devices. And we are looking at 2023, 20 billion connected IoT devices through the networks. But this is only one part of the evolution that is ongoing. I think this is even more interesting, and that is the embedded world. We are looking at a hockey stick evolution here as well, both on the sensors, because what is critical is to capture and measure properties of the physical reality. So we're looking at the sensor technology evolution, that we have MEMS and we have nanotechnologies, etc. The costs are dropping tremendously, and the sizes are dropping tremendously. It's like 30% per year. So you can see that this sensor on the match here, that it is a gyroscope and accelerometer, and they cost nothing. And the other evolution here is on the processor side. Companies like Intel have been pushing multi-core processor, new architectures, etc., to increase the speed and increase the number of instructions processed per second, and so on. But there's also another evolution that is driven, I would say, by a company called ARM. We all have ARM processors in our pockets because they are in all our smartphones. How can you make the processor smaller, lower cost, lower power? And now the latest thing that is happening, that you get this kind of lightweight AI capabilities on these microcontrollers. Here I'm talking about 16 and 32-bit microcontrollers. It took ARM 22 years to ship 50 billion of these chips through their ecosystem. And it took them 4 years to ship the next 50 billion. And now in the coming 4 years, they are projecting that they will ship 100 billion more. And the majority of these ones will actually be connected, and they will be embedded in cars, in buildings, and what have you. And you see the tiny speck on the golf ball there. That is a 32-bit microcontroller that is capable enough to host a web server. You can speak HTTP type of protocol to this kind of. It's not like it's the opposite of a large data center with tens and thousands of high capacity processors. Just to give an example, this is a couple of years old. It's a Samsung Gear Watch, about $200. The kind of wearable that you have on your wrist to measure your activities and pulse and so on. So $200 was the recommended retail price. I think it was like 4 years ago. If you tear it apart and look at the bill of material, So you have Wi-Fi, you have a gyroscope accelerometer, so you have these bunch of sensors, and then you have this CPU or the microcontroller, and you see that the total bill for all the valuable stuff, the electronics, is less than $10, and then you just add some plastic on top of it. So this shows, that we have now at our hands, we have the connectivity and we have the embedded technologies to actually make some good stuff out of it. Now, IoT, what is that? It's actually something that is transforming industries and transforming how business are going to be conducted. We talk about digitalization that is very much hyped. How do you go from, analog products to digital products? How do you go from manual labor to digital labor? We also talk about servitization, how instead of selling a product, we sell the outcome of the product. So IoT is about embedding these kind of capabilities in how you can make, inanimate objects and things in like my teacup here, make that behave in a smart way. So we're talking about the physical products, we're talking about physical infrastructures, it might be utility grid or whatever, but we're also talking about the processes associated, and this will enable business transformation. So moving to, one example of that I think was the first one, and it's a pretty interesting one, how technology enables business transformation. It's the music industry. We used to buy physical products with analog content. The next thing that happened was that the content was actually digitized instead of analog format, digital format. So we bought a physical product with digital content. The next thing that happened was that we didn't buy a physical product, we bought a digital product with digital content. And now we are not buying a digital product anymore. We are subscribing to the music instead, with companies like Spotify or Apple Music. So you see this transformation from physical products, from analog to digital, from physical products to digital products, and you buy a product that is an MP3 file, or you listen to the music via subscription, meaning that you don't own what you have, you don't buy something, you're actually using a service instead. And the ultimate thing is, I added SoundCloud here because it's quite interesting. So this is like a transformation journey, and what does that mean for business? If you look at the value chain in the past with the typical vinyl records, there was a bunch of different companies involved. The record company, there's a publisher, there's a distributor, retailer, so before you actually get your material. Today, with SoundCloud, I can be an artist and I put my stuff up on SoundCloud and the listener can get there immediately. So you see a complete collapse of the value chain, and a lot of companies have disappeared and a lot of new companies have grown out of this. What does that mean for IoT? Well, product as a service is something that, this is like an Electrolux washing machine that becomes digital and it becomes connected. And product as a service means that you don't need to, as an end user, you don't need to pay for buying a washing machine. You pay per kilo of wash that you do, or you pay per the type of washing program that you do. You can optimize energy consumption from an end user perspective, and it never breaks down because it will always be fixed by the owner, because it will still be owned by the manufacturer. The supplier, on the other hand, builds customer experience, it gets stickiness to the customer, it builds a brand, you have recurring revenue without the W, and then you also understand how the product is used in the field throughout its life cycle, which means that you can improve quality of the product because you get data continuously about the usage of the product and the behavior of the product. Another example around that was like a connected product or software defined product, but the other one is how do you actually change business processes. This is an example from utility industry. We used to have these meter reading cards that you fill in the water consumption or the electricity consumption. This was very bad, costly, it's manual, you need to handle things. People could cheat, and if you get the card, you're lucky as a utility. If you don't, then, well, what do? You send out the person, that's costly as well. But now we have these remote meters. Everything is automated, it's accurate, it's secure, You can do meter readings every 15 minutes. You can profile the usage of the energy consumption, because you can detect if it's the washing machine, if it's the oven, if it's the refrigerator, and so on, and send that information back to the customer. So there's a lot of benefits here. So now, is this important? I will flash this very quickly. There's a lot of money. This is the transformative value of IoT. It's not the value of software or device sales, but the transformative value of IoT, how it actually impacts a number of sectors across. And you can see by the numbers here that in 2025, we talk about over $10 trillion per year. And if you look at the annual gross domestic product, the global one, it's $90 trillion. So it could be as high as 10% of the global GDP, the turnaround of the planet. And this is why also there's a lot of focus, and players are actually moving into this space. And you can see that the manufacturing is one of the big sectors here, factories. There could be discrete manufacturing of products, or it could be process like a paper pulp or oil and gas and what have you. But there's a lot of money at stake, and there's a number of benefits, not only monetary benefits, but also sustainability, for instance, in precision farming, and reducing the leakage of fertilizers and so on. So is this something that is completely new now that is happening? Well, it's not something that comes out of, as a strike of lightning from the sky, but it's actually, if you look at the origin, it's actually an evolution of a number of different disciplines that have been around for years. From a communications perspective, we have been talking about machine to machine for about 15, 20, it has been around for 20 years at least. But now that is turning more into the internet. We are talking about industries, operational technology, where you have programmable logic controllers that sit in heavy machinery based originally on analog stuff, being some of it being digital, and you have some control loops that might be analog processing, analog circuitry doing it. Now we are replacing it with digital circuitry and instead. So the automation industry has been doing this for decades as well, but they have been doing it in their own way and with old technology and so on. Now they're looking at how can we move to use digital technologies, what does the internet mean, and so on. I met with a large Swedish company based in, well, it's half Swedish, half Swiss, based in Västerås. And when was this? About 2014, and preaching, look at using internet technologies and the IP stack, and they say, no, it's not secure, it's not capable. Now they are completely onboarded on that. So we see that more and more. It takes time, but it's happening. And then we have the evolution from wireless sensor networks and embedded systems, control systems. We talk about cyber physical systems that come from more the embedded world into IoT. And then we also have a big explosion in interest now to use AI. It used to be big data. Now we talk more about AI and machine learning. But these are all disciplines that are coming together to actually shape what is IoT today and how IoT is going to be evolving. So IoT is basically how can you create a digital representation of the real world? This means that, so now I'm not talking about the devices, I'm talking about what can you actually do. If you look at buildings, for instance, you're interested in understanding the workings of the building, that the comfort for people, the air quality is good enough. You want to have the heating on when there is needed to be heating in office buildings, and when people are not there, you can switch things off so that you can save energy. You want to save water. How do you replenish paper towels in bathrooms and soap dispensers? All of this needs to be automated and becoming more efficient. So you're looking at digitalizing the entire building so that you can basically look at what are your interests and concerns about the building so that you can optimize those workings using digital methods. So buildings and bridges, and you have these kind of heavy factories and oil refineries. You have the personal aspect. When I'm out skiing, I always carry my gadgets around me to keep track of how I'm doing and if I'm falling or not. which I usually do, or you have the trucks, and I mentioned precision farming. So this digital representation of the real world, that is what IoT is about. So it's not about connecting devices and getting sensor data, but it's to digitalize the real world. So how do you do that? What does a IoT solution blueprint look at from the top level? This is I put today because I think that we're going to be seeing some changes here in the way things are done. I mean, at the bottom we have the things and the people, etc., that we want to understand the workings of, and for that I mentioned we have devices, we have sensors that measure properties, temperature, humidity, air quality, particles in the air, vibrations, what have you. You have actuators that makes you be able to control what is going on. Like if you have if you have diabetes and you have an insulin pump, you can control the pump that is injecting insulin to a person. So that's the actuation part. So it's like you have your eyes and your ears to feel things, and then you have your hands to actually tweak and fiddle with the physical things and change their properties and change their behaviors. And then you have tags. We talk about RFID, we talk about QR codes and so on, that you can put identities on stupid objects or inanimate objects, I should say. Then we have connectivity, and there's going to be a plethora of different connectivity means here. It could be local, you could have direct connectivity, you could have wide area connectivity using cellular technology, you might have satellites because you have a gas field somewhere in remote parts of Russia, or you have a mine remotely in Canada. Then we have cloud, and we need to have data management. How do we handle the data? And cloud is typically the virtualized environment where we put our software in what we call an IoT platform. And this is one of the things I think that's going to be changing, because today we're looking at IoT platforms on top of connectivity, something that is residing in a data center that has some capabilities for managing devices, collecting data, doing some rudimentary application logic on data, and we're exposing APIs towards a set of different applications. That these IoT applications then needs to be exposed to people, like alarms. I get my dashboard for my fitness, my runs or my bike rides. Or if you're an enterprise, how do you integrate this into the ERP system, enterprise resource planning system, or a customer relations management databases and so on. So you have this kind of exposure. So this is typically what the IoT solution looks like: devices, connectivity, an IoT platform, and then applications on top of it. So as you can see, IoT is not a single technology, it's actually a technology stack. We have the devices, as I said. There's some stuff that is important here, and that is that we need to solve interoperability. I will get to that. And we need to be able to have massive scale devices that are unattended by people. Security is going to be critical, and we need to understand that we are not securing just the connectivity or not just the device, but we need securing the application, the data, and so on. I mentioned connectivity, I mentioned the cloud part, and then AI is going to be the central part in how you actually extract insights from the data that you're collecting. How can you actually do self-learning system and adaptive system? There's a lot of control and there's a lot of automation. It's not just getting data up and then understanding it, but you need actually to act on it and send control commands back into the physical reality. So I will go over a couple of these ones very quickly. One thing is around IoT devices. Some of the current issues with IoT devices that we've seen for a number of years, but it's still here. Usually, when you buy, when you get the device, usually you get one app for that. So if you're buying something for your home, a lock system, or a wearable, or water boiler for the basement, for the heating system, or whatever you buy or any kind of appliance, you buy this gadget and then you get an app in your mobile phone. So this one device, one app needs to go away. We need to treat devices more like that they are exposing their capabilities, but they're not hosting the application itself. They just need to expose, this is the data, these are the capabilities that I have. So if all the devices actually do that, then expose that through a set of APIs. Then on top of that, you have a rich set of data where you can build applications that are tailor-made depending on your needs. There's also a lack of interoperability, and I will get to that one as well. And this lack of interoperability is actually a big problem in terms of let's say, vendor lock-in for enterprises and so on. And there's actually a lack of value that you can extract. I think that there's this report from I think it was McKinsey, like 1% of the data is actually used. One of the big problems here is the interoperability. 40% of the value is lost because you lack the kind of interoperability. And then the next thing is that you have this kind of manual provisioning. There's always a person that is available to reboot a device, insert a SIM card, to pair a device to an application, or pair something to a network. So these are some issues that we need to address. And the first thing, and this is a really old slide. I've been using this for 10 years. It's still valid, but we are getting somewhere here. First of all, as I mentioned, if you're looking at different sectors, and here you see a set of standards, KNX, Z-Wave, Loanworks, BACnet, XMPP, Zigbee, and there's more, X10 and so on. They're all standards in one sector, and that is building automation. So even if you go to one industry for one use case, which is building automation, you have a set of standards, de facto standards, and proprietary technologies from big companies. So if you buy building automation equipment or something that needs to be integrated, you're stuck with one supplier, and this is really a problem. So what you need to do is to use IP, because very few of these are actually, if you look at it historically speaking, are based on IP. So we need to use the internet stack. And we need to drive it even down to these kind of, let's see if I can show it, this kind of, this is a microcontroller. This is actually an IoT device. I can get it in front of the camera like this. It has around 10 different sensors. It can host a web server, etc. And this is where we need to get to, a 32-bit microcontroller. So we can put these web service stacks onto these microcontrollers. People were claiming that was not possible in the past, but it is now. The next thing, once you get IP, we should actually use standard web technologies, like HTTP kind of way, the way that we are programming the web, so that we have REST APIs and we expose resources as web resources. And this goes into the data models, etc., how you model data that are exposed for applications to actually use. Not only is it so that, programming, if you're stuck with these plethora of different protocols and technologies that are proprietary or industry specific, if you want to build applications on top of it, there's very few companies that can actually do that. And mostly the companies that sell you the product. So it's going to be very costly. But if you go the web way, you can take any web developer from the street, can actually get going in a couple of hours to do the programming. And then, since if you look at an IT environment in an enterprise, that is also web services oriented and web based. So the enterprise integration is going to be very, very smooth. Now the world is getting in this direction, but it's really solving this kind of interoperability across the stack. Once we get IP, we should go for the web, but there are still protocols like MQTT and AMQP, etc. around, but that interoperability can be shown or be proven, and then also how we expose the resources on top, and adding them not only how you format the data, but also the semantics. What is the meaning of data? Because if you add meaning so that software can understand the meaning of the data, then you don't need to have any kind of manual process in figuring out, okay, this data comes here and this tells me this. No, the software will figure that out because you're adding semantics to it by semantic tags and semantic web technologies. This is something that we have been driving for many years in standardization, and this is now happening big time. And you see some of the organizations there, the logos of them. And as an anecdote, you know, we have done this work for a number of years, as I mentioned, and a colleague of mine, he when this IKEA Tråd-free product was announced, where you had these smart light bulbs and remote controlled and an app in your phone, etc. Then he tried to figure out, okay, what does it actually contain? Well, it was built on the technology that we have been developing and been standardizing in IETF. And IETF is the global organization where everything around internet is standardized. So all the protocols, you know, the mail protocols, web protocols, TCP/IP stack, all of that is in IETF. We have been pushing this kind of lightweight web, let's say a binary version of HTTP that fits on microcontrollers. And we have been defining this set of simple data objects for temperature, humidity, luminosity from a lamp, switching lamp on and off, etc. We have been standardizing that in IPSO Alliance. And then he discovered that, yeah, IKEA, we have been talking to IKEA, but we haven't been pushing this technology. But they understood the value of it. And they said, this is good. We're going to be piggybacking. We're going to be using this in our products. So they discovered the value themselves around this kind of embedded web and the ease of actually doing things. So I think this was a very good proof point. Now, moving on, security is critical, and especially if we're looking at deployments in tens of billions. I mean, if you look at a car that is manufactured in Japan and it's sent somewhere globally to any country in the world, how do you actually make sure that it can connect and bootstrap itself and download new firmware and so on? Or if you're buying a gadget using some kind of connectivity technology, when you open the box here in Sweden and want to install it, how do you actually secure it? Well, there's a lot of manual labor. If we're going to be having tens of billions, or looking at the ARM number, if you're going to be having hundreds of billions of embedded devices, and note you, many of these devices will be embedded in places where people cannot go. Meaning that once you deploy it, it's going to be stuck there and you can't go there, you can't reboot it, you can't open it, and so on. So how do you actually do this? And this is one of the issues that we have been working as well with partners, ARM being one of them, that if we can secure the entire life cycle of a device, usually we are looking at the step where you see users and providers. This is where you unbox, well, you unbox and then you switch it on, and then you provision it with some information, SSID for Wi-Fi or whatever it is. But actually, if we can secure it even from the manufacturer, not when you manufacture the device, but when you manufacture the silicon, the chip. Now we have these kind of trust zones in application processors that are secure environments where you can put the credentials, cryptographic material that can prove the origin. And then you build this kind of, that is going to be a root of trust, and that can be used to bootstrap other credentials like passwords to Wi-Fi access points, or credentials used for securing data, so that you can actually have this kind of multiple identities depending on if it's the connectivity, if it's the device itself, somebody needs to manage it, and only that person or that organization shall do it. On the other hand, the application data is owned by a third party. How do you secure all of that? Well, you need to secure it throughout the life cycle. And you should start with a chip where you have this root of trust embedded, and from that you can spawn new identities. And then at the end, 20 years later, by the way, 20 or 30 years later, you discard and you decommission the device. You want to decommission it securely and make sure that any kind of cryptographic material is properly trashed. And this needs to be an automated process, no manual intervention as part of this. Like inserting SIM cards in cars in Toyota's factory in Japan, a company that we are working with. So this is super critical to get this going, to actually get to this massive scale of hundreds of billions of devices. Another thing that is very important is that we're looking at pushing data from the device to a data center for processing. Now we're going to be seeing, with these tens and hundreds of billions of devices, we're going to be, that was my gadget buzzing me. We're going to be seeing data processing taking place closer to the source and closer to where data needs to be consumed. And we need this because of performance, short latencies. If you're looking at the factory and you have this kind of control loops, we can't pull data to data center and then send down a control command. So the latency and the reliability is driving this, and also safety, because some of the applications, if people go into a factory where there's robots working, the robots should shut down immediately. And you can't depend on this happening in a data center with some flaky connectivity perhaps going on and restarting on stuff. Some of these applications need to happen locally on the shop floor inside the factory. So there's a number of these different drivers. So the IoT edge and edge computing is also very much hyped, that this is going to be, this is happening now, and the IoT edge. And another thing that is very important here on the right-hand side here is data itself. When it comes to data management and the IoT edge, we need to clean data, because data can be it can be contaminated and it can be unclean. So we need to clean data. Sensors might be miscalibrated and so on. So cleaning the data and curating the data needs to happen at the ingress of the network or of the system. And we need to ensure provenance, so that you know where is this actually produced, this data, so that you have proof of the source, so that you don't get fake data into the system. And then adding, as I said, semantics. So all of these are steps that needs to take place before you apply AI or any kind of machine learning on top of it. I need to get to the connectivity part. How am I doing with time? The connectivity part, we are now in the process of rolling out 5G, and I should skip to this one perhaps, that we are used to mobile broadband, but with 5G we are not only doing enhanced mobile broadband with higher speeds and higher capacities, we're also going into what we call the critical machine type communication, where we're looking at, ultra low latency. We're talking about millisecond latencies, extremely high availability, upper bounds on delay variation of data that is sent, because we want to be able to control industrial robots or planes, or any kind of remote monitoring of or remotely controlling mining machines from an operation center overground. And then on the other side of the spectrum, we have this massive scale where we are actually taking cellular technology even down to the tiniest low power applications like logistics. We have containers, and we have cellularly connected devices that can last 10 years on a battery. So that kind of application space. So this is what we're seeing is happening now. We are rolling out with 5G, and in research at the same time we have of course started to work on 6G now. But as I said, the majority of value comes actually from the IoT data. And if you look at what you want to do with, hold on 2 seconds, I need to check the time here. 5 more minutes. So if you look at the different types of applications, and if you're going to be using AI, you need to understand that it's not just one single type of problem that you're looking at. You might have you might be looking at how can I understand and forecast climate change or soil erosion, or how water is actually, groundwater, etc., is behaving depending on seasons, rainfall, etc. And then we are looking at this massive monitoring, and we're looking at from past data, large amounts of data, looking at statistical and probabilistic models on understanding and forecasting things. How are things actually feeling, and what might be possible futures in this space. We're looking at another problem is like we have infrastructures. If you look at the smart grid or if you look at the transport network, how can you direct traffic in a grid of streets, or how can you direct electricity in a grid of transformers and producers and so on. So this is more like the previous example was more like, yeah, you're looking at data, trying to understand it. Here, you're looking more like you get data in, you need to understand what's going on, and you need to control stuff. And it might be very complex control mechanisms that you have in rerouting, in water grid or electricity grid. It's like this kind of smart city kind of setup where there's a lot of infrastructure that is interplaying. Then you can look at these isolated assets, whether it's a jet engine, where you want to do predictive maintenance. You want to understand from every flight, you download, extremely large amounts of data actually from the jet engines, trying to understand the health of the engine. Or you're looking at these kind of buildings where you also have this kind of control, automation and control. We're looking at logistics. Logistics is another type of problem, because here if you're looking at emptying trash cans in a city, then it's a lot of planning that needs to be done. You need to measure, what's the fill level. That is one thing. And then based on the fill level, do you need to empty it or not? And then you need to have the truck that is running around picking up and emptying trash in trash cans. How do you make the optimal route? And so this is more like a planning type of problem rather than sifting through large amounts of data. So you have a set of these different kinds of use cases of robots as well. And you might even have these kind of device swarms that are behaving, or they are basically having a collective intellect altogether. So there's not a single AI algorithm that is going to solve all of this, but you need actually a set of different tools. So you're looking at this kind of massive amounts of data. You're using data science and analytics, and then you have the other end of things, which is more like around facts and knowledge and logic and reasoning. So you have this set of different tools in your toolbox that you need to combine and looking at depending on the problem that you're solving. And also adding to this, AI, believe it or not, but there's a lot of hype around AI. AI is not going to be able to solve all the different problems, because what you actually want to start with is models based on natural science. So you start with a physics-based model, and when that fails, you might revert to, well, not fails, but how you can use AI to actually tune that physical model. So this is the set of different algorithms and models that we need to apply in IoT to solve the vast plethora of different problems that we are looking at. This is the final buzzword that I'm going to be talking about, and that is the digital twin, which is basically IoT platform 2.0. A previous platform, the IoT platforms of today, they are basically, we are collecting data from devices and so on. With a digital twin, we are actually doing this kind of thing of creating a complete digital representation of the physical entity. So a digital twin has, its other twin is the physical twin. So where you are actually looking at the physical twin from the perspective of your interests and not what data do I have. And this will be, we will be breaking these kind of data silos and removing the problem of interoperability and reducing cost, because we're reusing data much more widely. So digital twin is going to be, this is what is hyped just right now. So, and then I had a couple of examples, but the time is running up. One is Industry 4.0, process manufacturing, and everything in the factory will be using IoT for robots, for logistics, for automatic autonomous guided vehicles, and monitoring what is going on in the production environment. I mentioned precision agriculture, both from yield and productivity, where you actually do fertilization and irrigation down to, let's say, the meter level, depending on the quality of the soil. And then the last example is a smart grid, where we're looking at renewables, moving away from big power stations generating electricity for millions, but we are having millions of power stations or electricity producers. And how do you send all of that energy around in the grid if it's a complete mesh of consumers and producers, and then adding storage of electricity in electrical vehicles and in buildings using batteries and so on. So these are three areas where IoT is going to be, or is, extremely central. So I will end there. Digital transformation, IoT is, I think one of the most impactful transformation agents, best thing since sliced bread. Connectivity, embedded technologies enables this, but the value comes from data, reasoning, and automation using different models, including AI. And now we're actually on the brink of getting this up and running. We have been for about 10 years doing a lot of proof of concepts and trials and so on, but now it's actually scaling up, and that is why there's no more venture capital in the IoT space, not that much anymore, because it is about to be productive. So with that, I thank you. I want to make an ad for a book that came in the second edition a year and a half ago, I think, or 2 years ago. It's an IoT book that covers everything around why, what, and how. And if you're interested in what Ericsson is doing, you can follow us. So thank you all for this.
All right. Thank you very much, Jan. Do we have the slide for the course? I'm just going to. So if you want to ask some questions for Jan, you can do that on the Menti. That's probably been seen during the presentation. So write your questions there. And I'm just going to sort of say a little bit about this course that is starting. So this open lecture here was actually also like the first lecture of this course. So we're starting a course that will be on, the focus will be on IoT protocols. And this course is actually still open for enrollment. So you can enroll on this course. So if you thought this topic was interested and want to know more about Internet of Things, you can actually enroll for this right now. But you can sort of only enroll like today or tomorrow. So you have to hurry up a little bit because the next lecture actually starts on Tuesday. This course is a little bit special because it is a 3 HP course, so it's not very sort of big, but it's split over 10 weeks, and it actually, it is made for working professionals, so that someone can take this course as they're working, just to sort of further educate themselves and learn more about Internet of Things. And it's free of charge, and it is available on this on our website here. You can find the link to antagning.se where you apply for it. And the course is in Swedish actually, so it's even though this lecture here was in English. All right, so I have some questions here, and maybe some more will pop up since I know there's some delay on the live stream. First of all, I got a question probably from one of the students that already is enrolled on this course, that will this session be recorded? And yes, it is live streamed, and it will be still available on YouTube afterwards. So we have a security question first, Jan, which is quite common when we talk about IoT. So it says, like, with a world which is more and more connected, especially with industrial IoT gaining control over critical functions of industry, how does Ericsson work to secure their solutions?
Our solutions, we are primarily a provider of mobile infrastructure, and those networks that we have, they are secured, and they in all sense and ways. And looking forward, I think there's also a lot about talk about stuff like it's super critical. Everything that we're doing, security is built in by design. It's not something that we are bolting on afterwards. So security is where we are doing threat models around every aspect of our infrastructure that we are providing. We are also looking at let's say other things around trust, because it's not only security but trust. How can you trust the system? How can you trust the data? And these are key elements that we are building into our products. And then people might say that, and we know from the fact that the cryptographic algorithms, etc., that we're using that are industry standard, they are proven. But then people are also looking at, we have this phenomenon called quantum computing. How will that change how we actually secure things? And this is something that we're actually doing a lot of research on. So I would say that, I mean, security is the first question that people actually ask. So rest assured, we are on top of it.
Yeah, I know being an IoT researcher myself, I also know this question always comes up. But connecting to that also, actually, we have a follow-up on this, is that you mentioned that it was difficult to convince a company about using sort of the internet in 2014 because of security reasons. Could you talk a little bit more about what has changed since then regarding the security aspects?
Well, the opposition was that internet is not secure, and internet wasn't secure, and it still isn't secure in many aspects. But you have to differ between how it's actually used and what the technology actually is capable of. And I think that there has been a lot of misunderstanding here. Everything, you know. You can't trust the internet, you can't trust the web. But it's more, that problem comes more from how it has been used. And since then, you know, security is one of the key areas that is happening around the evolution of the internet itself. And there's a lot of research, there's a lot of standardization going on. But even back then, I would say that the technology itself was secure enough, and it was not only security; it was also performance. It's too costly. The processors to run a TCP/IP stack and to run the applications on top of it, it would be too expensive for their equipment. But I think that has also changed, as I think I've proven. So I think that now. And also these companies that have been in opposition, and even those standards bodies like Zigbee and so on, that has been we have our streamlined protocol stack, we don't need IP because of X, Y, and Z. They have also turned around. So now you get these standards, they are also evolving in the IP direction, TCP/IP, and also embracing the web technologies that I've been talking about, like the binary HTTP kind of thing.
All right. I also have two questions here, more on the things side or the device side. So it says, like, I suppose that many things will be retrofitted with IoT rather than redesigned from scratch. What is your perspective on these IoT functionalities and how they will be electrically powered?
There were two questions there, I think. Well, there was a statement first, and I totally agree to that. People are looking at, if I need to modernize a production line, or if I need to modernize something, do I need to buy new stuff? No. And I think that this kind of retrofitting is something that people are forgetting. There's an interesting, from the Industrial Internet Consortium, there's an interesting white paper on this topic that I think it's called nurturing a green patch in a brown field. We talk about brown field and we talk about green field. So read that white paper. It's actually good in understanding that you can prolong the lifetime of your products and your equipment by retrofitting. And power is, of course, something that is important. And usually for the kind of equipment that we're talking about, there is power available because they are powered themselves. And then we have, of course, things can run on batteries, and with microcontrollers, the way that they have evolved and these devices, depending on the application, of course, you can run things on years on batteries if they are small and power is a problem. Another aspect that is happening that is more, perhaps, let's say, still on the research or more on the innovation side is energy harvesting. How can you harvest energy from the environment, especially if you're looking at these tiny sensors that you can put onto things. If you're looking at measuring, let's say, how wheels, going back to the SKF case where you're looking at roller bearings used on trains for the wheels, then you can actually mount sensors that measure the vibrations, and they are powered by vibrations. So the only thing you don't need external power, you don't need a cable, and you don't need a battery, but you need to be able to store energy. So you can harvest energy. But it all depends on if we're looking at the big machines and the complex devices, or if we're looking at these more tiny things that are more telemetry oriented.
Yeah, all right. We actually have a follow-up question on that as well, but it's more sort of like connected to the bottlenecks, I would say. So the question is, we can inject sensors and hope for a unification of standards on communication, but where do you think the bottleneck lays for industries to step on and embrace data-rich and online production strategies? They also said, like, related to this SKF case, for example.
You know, there is a set of hurdles. One is, you know, it's still this interoperability thing is one of the issues, because suppliers have their own standards, and the entire stack is very fragmented, especially if you go to the industrial sector. If you're looking at field bus technologies and so on, there are 16 or so different versions. And to get Siemens equipment to talk to Bosch equipment, to talk to ABB equipment, that was not, at least a couple of years ago, that was a big no-no, because we have been trying to work with all these companies in saying that if you go state-of-the-art, you will open up a much larger market because you will enable an interoperability jointly. So don't take technology as the fight, take the fight in the market instead, like we have done in the mobile networks infrastructure. Basically defining the technologies together with our competitors. So the interoperability or the lack of interoperability, and because there is inertia in making this kind of transformation, you need to capitalize. It's return on investment. You want to capitalize on the investments that you have made and not erode and cannibalize on your own business. So you need to move in a controlled manner. That, I think, is one of the things that the companies are doing. The other aspect is, of course, also around data ownership. And if you look at manufacturing and data, there are two aspects here. One thing is there's some data that should never leave factory floor. The factory floor itself there is a demilitarized zone to that, into the enterprise IT system. And then there's another demilitarized zone as you enter, let's say, the internet. So there's two layers of security perimeters here. And some data should not leave factory floor, full stop. Should not even go to the IT department, not go to the other departments inside the company, but maintain. And that is one of the things that Industry 4.0 is looking at, you know, if we want to have this kind of mesh way of building factories and reconfigurable factories. The other one is also data ownership, that data that is collected from an industrial machine. Who owns that data? Is it the one that is owning the process that is ongoing on the factory floor, or is it the company that built the machine itself? Because the data that is coming out is also telling the behavior of the machine and how it's built. So, you know, this is a little bit of a tussle, and we have encountered that when we have been talking to our own factories. Ericsson is a manufacturer, so some data cannot be exposed because the machine manufacturer will not allow us to see the data. So there's some issues here to still work on to move on. Yeah.
All right. So the next question is a little more towards the machine learning part, which you touched upon a little bit. So what does machine learning represent in the IoT from an industrial perspective? And you talk about web-based control systems. However, critical machines in industry need real-time action. How do we sort of implement this type of control using AI, machine learning, if we need real-time systems?
I can give you one example, and that is you can read about this also on the the Ericsson blog. It's something called TinyML, so tiny machine learning, and how you can actually deploy algorithms, because there are two aspects to the machine learning part. One is one aspect is the learning, and for learning you need data, and data you can collect from many sources, and you will do that offline, and you will do the training of the models and so on. But once you have them, you can actually deploy these algorithms locally on microcontrollers even, so that you can have this kind of control loop that is very much embedded into the factory environment, using this let's say concept of TinyML. And that means that these are algorithms that can sit on 8, 16, 32-bit microcontrollers. So the learning takes place somewhere else. The algorithms are then downloaded onto the microcontrollers. And TinyML as a service is a concept that we are working on, where you use the kind of web protocols to actually deploy these algorithms. I hope that was an answer to the question.
Yeah, no, it is. And at the same time, actually, I can make some more advertising for more of these courses that we are also giving, because one of the courses we are giving is on sort of applied machine learning. We don't have time to go into TinyML in that course, but we have this type of course like this one also aimed towards machine learning. And this is actually also connected to the next question, which is more of a 5G question, because we're also starting a 5G course similar to this one on IoT, but on 5G after Christmas, basically. So the 5G question is, what are your views on the 5G in the context of roaming between countries with varying political stability? How can I be sure that my 5G connected device, like a car, will be working in all countries?
This is definitely high on our agenda, and we have been working on this for a number of years. I mean, we already have roaming and so on, but what we're talking about is when things are roaming and on the global level, and how can we, especially when we're talking about these kind of things that you're selling it on one market, and it's not like, I mean, in Europe we have the roaming agreements that makes us able to roam across Europe with a decent bill coming back. But for 5G, and if we talk about IoT, and if we talk about connected things, this is definitely a critical issue, and we are working on this in together with operators, because basically what you need, that if you have a set of operators that have their own networks deployed, we are looking at providing a service on top of that actually unifies connectivity for exactly these things around connected cars. And that means that we're building a kind of ecosystem of different operators, but providing this unifying platform on top. There is an industrial consortium that's called Aecc, Automotive Edge Computing Consortium. They are, and we are part of that, and Toyota and some other big companies. And there are white papers there that actually explains this in more detail, if you want to read more about it. But it's for sure happening. There was also some geopolitical thing in this as well, but I don't want to go into that.
Okay, all right. So thanks very much. I think that's all the questions we have and we have time for. So again, I just want to highlight that we have this course on Iot Protocols that is coming up, that you gladly should look into if you want to know more about Internet of Things. And like I said before, it is a 3 HP course over 10 weeks. It's made for working professionals, so it will be sort of slow speed. Will be very flexible in terms of recorded lectures and stuff like that. And there's also like a win-win situation. If you're working, you can actually do like an IoT project in the course, so you can actually benefit in your working situation. Easiest is to find it on our website, www.mion.se/iprof, where you will find all of our courses, this machine learning course and the 5G one as well. But you apply for it on antagning.se. All right. So thank you very much, Jan, and thanks to everyone that has been online and listening. And yeah, thanks.
Thank you.